All right, so I promised I'd get into some practical diagnostics. I think I saved this for the end of the course. It's a good place to finish up with, because it really starts to, we're going to look at some real data and look at some real practical examples. And I want you to get a feel for some of the things that we really have to look for in the data, and some of the things that we can learn every time we look at a data set. And, you know, at Fiquet, we've really learned this through experience. We've looked at thousands of production data sets over the years, and every time I look at a new data set, I learn something new. The data really teaches us how to analyze going forward, and everything we learn, we put it in our little toolbox, and now we have it available to use on subsequent data sets. But you don't want to get in a position where you're trying to paint all of these different wells and reservoir systems with the same brush and try to overgeneralize them. Because as I said, you're always going to learn something new. So you really want to treat these well production data sets as individuals and try and learn as much about each one as you can. Now, that's not always practical. We may not have time to do that. But certainly, if you're looking at a new field or high-profile wells, you do want to spend the time, particularly if you have the data available, you do want to spend that time to get as much understanding about that well as you can. It will pay dividends in the long run, because if it's early in the life of the exploitation of the reservoir and you want to understand how to develop that field going forward, you got to put in that work up front. Once you get to the stage where you're in development mode and you're drilling lots of wells, it may not be as important to look at every single one, and maybe you can apply more of a cookie cutter approach to your analysis. But I think we're going to need both of those techniques available, and certainly the practical diagnostics are important. And I'm going to talk a little bit about what these are, and then we'll go right into an example and show why they're so important. And hopefully I'll convince you of that. Diagnostics are a qualitative investigation of data. It has to be pre-analysis, pre-modeling. It has to be quick and simple. And it's a vital component of production data analysis. Obviously, any sort of reservoir engineering work that I'm doing, I need to be critical of the data that's coming in. If the data that's coming into the project is no good, then I'm not going to get anything good out of it, obviously. Garbage in, garbage out. Okay, here's a typical data set. Maybe not so typical, but this is real data. And a client had come to me years ago and said, well, I'd like to get an analysis of this data set. This is a gas well, dry gas well, producing very high deliverability, high gas rates, 5 million cubic feet per day, and we have our daily flowing pressures measured. At first glance of something like this, I think what you might notice, or what I noticed anyways, is other than the obvious, which is both rates and pressures seem to be flat, is that the data looks good. It looks good in the sense that the rates or the pressures are changing continuously, which tells me that they're being updated very often. You know, what I very often look for is a stair step. Stair step tells me that nobody's updating those rates or pressures. They're not being measured very often. So the measurement frequency here is not an issue. We're getting good quality measurements on a continuous basis. So I plugged the data into the program and did an analysis and found 90 BCF with virtually no evidence of any boundary-dominated flow or any decline. So it looked like a very, very large reservoir. The fact that it's flat here indicates that it's damaged. So it's probably got a high damaged skin, flat production. Haven't seen the boundaries yet. It's a very large reservoir. And I'm going to call that the face value analysis of the data. But let's go back. Okay, and this is probably the single most important diagnostic that you can do on production data. Production data, as I mentioned before, if we're looking at rates and pressures, which we always should be if we have the data available, is always going to come in a pair. Okay, there's going to be a time, and then there's going to be a rate and a pressure. And if the measurement is done properly, hopefully that rate and pressure are measured roughly at the same time. That's not always going to be the case. But in many cases, especially in SCADA systems and electronically measured systems, we're going to get the rate and the pressure at roughly the same time. So if we get a production rate and a pressure, the diagnostic that we should always do is look at them and see how they're changing with respect to each other. And there's two ways that this can, there's actually three ways that this can occur, okay? Way number one is that they don't seem to have any relationship to each other whatsoever. That's obviously not a good thing because you'd hope that your rates and your pressures are somehow related to each other. So that would be possibility number one. Possibility number two is they look like this and they track each other. Possibility number three is they track each other but in the opposite direction. Which one of those is correct? Obviously the third one is the one that you want to see. Right? Production rates and pressures should have an inverse relationship with each other. In other words, if the production rate jumps up, the pressure should go down to correspond, because we know that the way reservoirs respond is opposite to the pressure. If I increase the back pressure, I get less production rate. If I decrease the back pressure, I get more production rate coming from the reservoir, coming from the sand face. So this, when I zoomed into this little area of the data, this is the picture that I got. And so I immediately knew that there was something wrong with the data because I'm getting the wrong direction with my pressures. And what I found out afterwards is that the pressures, the rates are measured correctly, but the flowing pressures were measured on the downstream side of a choke that was on the wellhead. So if you think about it, if your wellhead is choked, and you're getting pressure measurements on the downstream side, these pressure measurements were actually the static pressures in a meter run. They are not in any way connected to the bottom hole. You're really just getting a sense of the gas rate that's in the system. As the gas rate goes up, the pressure will go up in the system. They're correlated with each other exactly. So that's not very valuable to me. That's not telling me anything about the sand face inflow, which is really what I'm looking for with pressures. I want to know how the operating conditions are changing. So, moral number one, or moral of the story, don't use pressures that are measured on the downstream side of a choke. In general, you want to use flowing pressures that are as close to the source as you can. What's the source? The source is the sand face. If your flowing pressures are far, far away from the source, for example, plant inlet pressures or something way down at the delivery point, the accuracy or the reliability of your interpretation will be very, very suspect. Okay? Now I realize that in most cases we can't measure, it's not practical to measure pressures right at the sand face. So we settle with measuring pressures at the tubing head or the casing. If you can get the quiet side measurement, in other words, the annular space between the tubing and the casing, in a well that does not have a packer in place, so we have a direct connection to the sand face, that's better. That's an even better measurement than measuring it on the tubing head side. But certainly we need it, if there's any choke or anything in place, we need it to be on the upstream side of that choke. So that diagnostic will tell you that right away. It's easy to see immediately whether rates and pressures are working for or against each other. Now again, there's other situations where maybe the data isn't measured this way. You might have daily production rates, but the pressures are only measured every week or every month. In that case, you wouldn't be able to do this diagnostic. So you may or may not have problems. Okay, so it's the diagnostics will really show you very quickly. It'll probably, if you're doing it properly, you'll probably end up with more questions than you had at the beginning. But certainly you need to investigate those things and make sure that you can make sense out of them. When the correct data were used in this case, as I found out later on that we had access to the tubing head pressures, but the field personnel didn't know what it was that we were looking for. So they sent the data, I suppose, that was easiest to get access to, or the data that they thought that we wanted, which was the meter run data. What I actually wanted were the tubing head pressures. Very clearly here it makes a huge difference, right? The tubing head pressures produce a clearly declining flowing pressure profile and completely changed the shape of the data. Now we're in boundary dominated flow. We only have 19 BCF. Dramatically changes the picture of the data. So if we hadn't done that investigation, we would have analyzed the data and come up with the wrong answer. Okay. The next step in this is to start looking at these sorts of diagnostics on log-log plots. And that's valuable for the same reason why it was valuable to look at data on log-log plots in the first place. We can learn a lot about the flow regimes and qualitatively what's going on in the data, because there's pattern recognition on a log-log plot that you just can't get on a linear plot of production data or pressure. For instance, this downward concavity that indicates boundary-dominated flow is very clear on this plot. The upward concavity that indicates the transient flow is very clear. So we're going to start to see, if everything was perfect in a perfect world, all the data should fit really nicely somewhere on that curve. Well, in reality, that doesn't happen. So there's some diagnostics that go along with that that can explain what it is that's causing that. Now, this work was done, with these diagnostics, was done a few years ago, I think in 2004, by myself and some colleagues at Fiquet, and we wrote an SPE paper about these diagnostics. I want to start, we can categorize these things a little bit. I want to start with discussing what I'm going to call material balance diagnostics. And the reason I'm calling them material balance diagnostics is because they happen over a long period of time, way into the future in boundary-dominated flow. Okay? Maybe not in the future, but in a long-term data set where we have boundary-dominated flow. These are diagnostics that take a long time to develop and are happening slowly, diffusively through time. They're not the sorts of diagnostics where you watch day by day and say, oh, my pressure dropped, therefore something's happened. These are long-term, low-frequency type diagnostics that we're talking about. And they're actually very straightforward. If I have my unit slope, the unit slope represents volumetric depletion. So this is, again, and we talked about this before, this is the harmonic stem for constant rate solution. And in order to do this properly, I have to plot the normalized rate versus material balance time on these type curves. So it's just the same as a Blassingame style type curve. So I can simply take my Blassingame plot the data on there, and if I see the data matching on that unit slope, that means I've got volumetric depletion. There are really two options that it could do that's different from the unit slope, right? One is that it could drop below, and the other one is that it could drift above. If it drifts above the unit slope, then that's an indication that I've got a reservoir with pressure support. So all of those cases that ARPS identified, such as multi-layer, solution gas, water drive systems, connected gas systems, composite systems, all of those sorts of things that can provide some sort of recharge over time are going to show data plotting out here, and you can do the diagnostics on this sort of plot. And it becomes very clear when you have systems that aren't volumetric. In other words, you're not draining a closed tank. You're draining a system that has some sort of influx on the boundary. So there's a boundary that surrounds this thing, and somewhere there's some fluid. We don't know what kind of fluid. We can only tell that there's an increase of energy somewhere occurring in that system. So we don't always know whether it's a water drive system, if it's a gas reservoir. Is it a water drive system, or is it gas that's recharging from a lower permeability gas system? We don't know that just by looking at this plot. We may need to use other information to evaluate that. On the other hand, if the data falls off the curve, that means we have a leaky reservoir. And leaky reservoir means interference. So that's where we have a situation where a well has been drilled in a volumetric reservoir, but later on another well gets drilled in that same reservoir, and so the available gas in place or oil in place for that first well is reduced. And that's our leaky reservoir. So both of these are very common, and the diagnostic is powerful because we can immediately identify whether that's occurring or not. We may suspect that there's interference somewhere, but if we don't see that diagnostic, then there's no reason to think that there is, or at least in a meaningful sort of way. Whereas if we see the diagnostic, then we know that there's something there. So what I'd like to do is show two examples of these things, one of each. So first of all, we will look at an example of pressure support. I spoke too soon. First of all, we will look at an example of a leaky reservoir. So this is our interference case. And this analysis was done entirely with public production data. So we made the assumption of constant pressures. We didn't have access to the flowing pressures. Normally, this would be a little bit dangerous because I've just finished telling you on several different, as part of several different discussions, that flowing pressures are very important. But in this case, we knew that the wells were operated at very high drawdown, and we knew roughly what the line pressure was. So we were able to predict the flowing pressures in this situation. In most cases, you'd want to have access to all those flowing pressures to get a more accurate interpretation. Now, in this example, we have 3 wells. It's a 3-well system. The first well came on production in late 1991, and then you can see there's a few years of production where nothing happens. And the blue curve indicates the aggregate production of the 3-well system. The red curve indicates the production just from well 1. So you can see there's 2 instances where wells come on stream, and the aggregate production of the system is increased quite a lot. And you can actually see the production from well number 1 starting to fall off. If we go to the analysis and look at the Blassingame plot, the diagnostic becomes very clear. Okay, our unit slope is shown in blue, and the interference is immediately apparent because the data drops off that curve. So that's the diagnostic. We can immediately tell, yes, this well is being influenced by interference from the offsets. What can we do about it? Well, there's some different things that we can do. Blassingame and his colleagues have proposed one method that we call a multi-well analysis, and the multi-well analysis allows us to correct for that interference effect. And what that's actually doing is it's changing the material balance time function. If you recall, material balance time is total cumulative production divided by the flow rate, Q. What if I were to include the cumulative production for all 3 wells? So it's now going to be the sum of all of the cumulative production of 1, 2, and 3, and however many other wells I have that I want to include in that grouping. So by doing that, you can imagine all those data points are going to be shifted over because the cumulative volumes are higher for the grouping than they are for the single well. And the thought is that if I've included the proper combination of wells in that grouping, then I should get all the data to fall properly onto that curve. If I haven't included all the wells for the grouping, then it's not going to work. For example, if I go back to the well manager and remove well number 3, so I'm extracting well number 3 from that grouping. And now I'm going to go back to the analysis page. You can see that there's a shift in the data, but it doesn't go far enough now. Okay, so the multi-well is being invoked here, but there isn't enough cumulative production to account for the shortfall that's observed in the production data as it falls off that curve. By the same token, as if I had put extra wells in there that didn't belong, the data would overshoot the line. So there's the right combination of wells that will imply a completely closed system. And that's the solution that I'm looking for. And that will help me establish what the total gas in place is for that entire system of wells in that multi-well system. All right, let's look at the other example. And the other example is for pressure support. This is a very different reservoir. This is a high pressure, deep gas condensate reservoir in the Gulf of Mexico. So you can see we have very high production rates. It's gas condensate, and during this producing portion of the data, we have really no water production at all. But we suspect that this might be a water drive system because some of the offsets have watered out. When we look at the analysis, and again, look at the Blassingame type curve, the effect here is a little more subtle, but it's unmistakable if you zoom into it and really take a closer look. Okay, so there it starts down the path of a unit slope, but then starts to depart, and that indicates the pressure support. So the pressure support is clear from here. What is it that's causing the pressure support? We don't know. There's not enough information here to tell me whether this is a water drive system or a connected gas system. Okay? But I do know that there's some additional energy that's coming into play here that's causing this pressure support. Now, I suspect that it's, as I mentioned before, I suspect that it's water drive because some of the offsets have watered out. That's why it is so important, so critically important to have an understanding of the whole field and not just look at production data in a vacuum. Because otherwise we wouldn't be able to make that connection and say, okay, this is what I think is going on. So what I've done here, you can see the data snapped into place. That's because I've already done the analysis, so I'm going to remove the analysis. But what I've done here is a pseudo-steady state water drive analysis. And the pseudo-steady state analysis is going to take the data and basically subtract the water drive effect to try and collapse the data back down onto the stem. It's pretty much the inverse or the exact opposite of what the multi-well model does. The multi-well model adds cumulative production to try and get the shortfall taken care of. The water drive is going to eliminate energy to try and get it collapse back down onto the stem in the opposite direction. And in the water drive system model, what we do is we can interpret initial water in place volumes and aquifer productivity index. And by fine-tuning those two parameters, we hope to get the best possible match of the data. So the way this works is I can increase the volume, and you'll notice that I can increase the volume. I'm not sure what happened there. Let's make that number big. I can increase the volume a whole lot, and in fact right now I've got 713 million barrels there, and nothing's happened. And the reason nothing's happened is because my aquifer productivity index is still too small. So I start to increase my aquifer productivity index, and hopefully I'll start to see an effect in the data at some point in time, and I can get the right sort of combination of parameters here to match that data. Now, it's probably still going to be some non-uniqueness. The initial water in place is quite high here. Let's try and lower it to see if it makes a difference. And obviously, I can lower it quite a bit. If I lower it too much, I start to lose the match. If I increase it too much, it becomes insensitive after a while. So I'm going to try and find that minimum where it just starts to depart and get it to match there. So I've now interpreted a combination of connected water, in-place water volume, and an aquifer productivity index that connects it to the reservoir. And that interprets the amount of energy that was available in this system that caused that diagnostic. So these are the sorts of things that we can include in the modeling, in the type curve modeling, to try and get a better match of the data and a better understanding of what's going on. Okay, so that's material balance diagnostics. Another area that's of interest is productivity diagnostics. Now, material balance diagnostics, as I mentioned, are long-term diffusive effects. Productivity diagnostics are usually going to be short-term, sometimes not, but usually going to be short-term and much more obvious effects. Okay? A material balance diagnostic is something that may take a long time to develop and may not be immediately obvious. A productivity diagnostic is something that's usually going to be very obvious. It's just our job to try and figure out what it is that's causing it. Okay, this is stuff that happens right near the well or in the wellbore. Material balance stuff happens far field, way out inside the reservoir. It's a quieter signal. This is a pretty loud signal. So again, here's our production type curve. And the sorts of things that we are interested in here is a well cleaning up. That's usually a pretty obvious signal. When a well is cleaning up, the Q over delta P, the production rate might be increasing and the flowing pressures might be increasing at the same time. Any single phase type curve will illustrate pretty quickly that that's impossible. That can't happen. Well, the reason why that happens is because when the well's cleaning up, there's relative permeability issues as completion fluids are being produced. And we're not modeling those things with these very simple type curves. The simple type curves assume single phase. So this is not going to match onto this. So that's our diagnostic. we can't really do anything about that until that data starts to peak and the cleanup issues are resolved, and now it matches on top of the type curve. That's the part where we need to focus on matching, and that's the part where we need to extract our reservoir parameters. And there's not too much we can do about this part. So that one you'll see quite often in the early time, particularly on wells that have large hydraulic fractures where you've pumped a lot of fluid into the reservoir and a lot of that fluid has to clean up. Liquid loading is another very common one that we'll see, especially in low rate wells, like tight gas wells, unconventional gas wells. And in liquid loading, we get a fall off that actually looks very similar to interference, but is caused by something completely different. What causes liquid loading effect is basically a buildup of water or condensate or whatever it is at the bottom of the well, and it just causes an additional pressure loss that starts to increase with time. And that additional pressure loss causes that fall off in either rates or pressures, and gives you that signature. So this one we can usually identify if we have enough information and we know the wellbore tubulars, and we understand what's going on there. Some other things that are commonly seen is if you get parallel trends in the data. We see that quite a lot. That could mean that something, at some point in time, something's happened. So the operator has gone in and done a workover or changed out the tubing. There's some shift in productivity, step change in productivity because of something that happened. Remember, a simple change in flowing pressure, step change, like putting a well on compression, shouldn't cause this. Because when I change the Q over delta P, or both the production rate and the flowing pressure, the net effect is that the normalized rate didn't change if it's just a response to a change in back pressure in the system. However, if I physically changed the productivity of the system by recompleting the well and adding more perforations, or re-stimulating the well, or putting in a new tubing string, I will actually get shifts in the trends of these things, and they're very easy to recognize. The final one that's shown on here is an increasing damage. This one is notoriously difficult to identify because it's something that happens slowly over time. And so it has the same sort of time scale as a material balance effect. So we often mistake it for a material balance effect. In other words, we may often see this as early depletion and mistake an increasing damage for a depleting well, when in fact it's not. It's still got lots of reservoir pressure, but it's just had a slow accumulation of damaged skin through time. So actually, let me start by showing an example of that exact thing. This is another high pressure, high temperature gas condensate reservoir in the Gulf, similar to the other one we looked at. This one's even higher, much higher deliverability, produces a lot of condensate yield, a little bit of water, and the pressures are extraordinarily high. I mean, we're talking about 11,000 psi of flowing pressure, 17,000 psi of initial pressure. In fact, almost 18,000 psi of initial pressure. So an extraordinarily overpressured reservoir. Probably, a psi per foot of pressure gradient, hydrostatic gradient. So we're looking at a very high overpressured reservoir. When we analyze the data in this well, this is the production data and flowing pressure data on the Blasingame type curve. The diagnostic would tend to indicate that we have a fairly well-behaved, boundary-dominated flow, volumetric depleting system. However, I talked about this diagnostic a little bit earlier, and that is the static pressure comparison to the flowing material balance analysis. And remember, I said earlier that we could sometimes see divergence between static pressures, which are shown here, and flowing material balance, which is shown there. all other things being equal, we would expect these to be the same. And the reason why they're not the same in this case is because we actually have a larger reservoir, but we have a declining productivity in the well. What we really should have in this case is an interpretation that looks like that. And now the shape of the data, of the flowing data, would indicate that the gas in place is much smaller than that. And that's because there's a whole bunch of accumulating damage that occurs through time. And we suspect that because this is so highly overpressured, that the reason for this is a compaction effect or pressure-dependent permeability in this well. If we now look at the productivity index of this one, we can see very clearly that the productivity index is a strongly decreasing function of time if we model it with the static pressures. Okay, so our interpretations sort of vary depending on whether we believe the static pressures or whether we believe the flowing pressures. Well, in this sort of situation, you have to believe the static pressures. And unless you think there's some error with the gauge, if the data is real, then you have to believe that there's that reservoir pressure is there, which means that the volume has to be there as well. In the flowing situation, there could be lots of different factors that cause that flowing data or flowing pressure to drop, accumulating skin damage, pressure-dependent permeability, all these things I talked about before, and that's why they don't match each other. So as one final thing, we'll do a quick history match of the data. If we do the history match of the production data and ignore the shut-in pressure, everything looks fine. But when we include the shut-in pressure, we can see immediately that there's a bust there, because our model would predict that the average reservoir pressure during that buildup would be in the region of 13,000 psi, whereas the actual pressure is more like 15,000 psi. So in order to establish a changing or accumulation of damage or changing skin through time, you have to have a buildup pressure. That's kind of the key thing that we're seeing here. And we've seen this in more than one well. We've seen this in other overpressured systems and other reservoirs. But it doesn't become obvious. If I didn't have this data, I wouldn't have been able to spot that. So the diagnostic, in this case, requires the presence of a buildup pressure. If I didn't, if I didn't have that, I wouldn't have been able to make that conclusion. And I would have interpreted the wrong volume in place for this reservoir. So that's the increasing damage. Let's take a look at a liquid loading example. Actually, to do that, I'm going to open a different file here. Sorry, it's not the one. Okay, this is the example I want to show. This is a tight gas well in onshore North America. Normally pressured, low deliverability. There are literally thousands and thousands and thousands of wells like this. And so there's lots of data that has this sort of appearance to it. The liquid loading is actually, you don't even really need to do the type curve diagnostic. You can see immediately from the sawtooth pattern of the production rates that this well is producing in an unstable manner. In other words, we have high production rates, and then they drop, and then probably pushes out a slug of fluid, and then it continues in that pattern. So that's the sort of thing, any operations person will know what that is immediately, and we can see that. But I want to show you what kind of impact that has on the type curve analysis if you don't properly account for it. So this is the data, face value, no filtering, nothing taken out, and that's the interpretation that we get. I've purposely matched it here in such a way that it shows the liquid loading diagnostic very clearly. But if you were an analyst that didn't have a lot of experience and you came in and matched this, you might be tempted to try and match that unit slope over here and say that that's boundary dominated flow. And that would be a mistake, because this data is due entirely to, that drop off in the data is due to liquid loading. So it's the reduction in productivity because of that increasing column of liquid inside the wellbore that's causing this behavior. It has nothing to do with seeing the boundaries in the reservoir. They're two totally different things, but they look similar on these plots. So that's why I bring it up as an important diagnostic. Now, there's a couple of things you can do about this. Both of them involve filtering the data. One thought is that you would just go through and do a filter, and I call this the eyeball data trend. In other words, I'm going to draw some sort of line through the middle of this, and we can do this systematically. You can do it manually, or you can run what we call a median filter, and a median filter goes through, finds that central trend, and eliminates all the scatter above and below that data. The other way to do this is to go through and pick out all the data points that have fallen below critical liquid lift velocity, and there's an easy way to calculate that velocity using the Turner or the Coleman correlation. And once we've done that, we can eliminate those data points. Both of those methods involve filtering the data, and I used the term earlier on reservoir signal extraction. Both of those involve a reservoir signal extraction. So what I'm trying to do is get rid of all the noise that's in here that's messing up my interpretation and be left with something that's going to show me the true nature of the reservoir. Just to be clear, this is a subjective procedure. Different people might want to filter it in different ways. So there may be some biases built in there. It's not always going to be an exacting kind of thing. But we all know production data analysis is a subjective procedure. It's not always going to be to the third decimal place every time. There's going to be some flexibility and that sort of thing built in. So this is the final result after we've done what I'm going to call the clean type curve analysis. I've extracted what I think is the reservoir part. I've eliminated all the noise that was in there. And what we see is there is actually, it looks like a little bit of a downturn in the data that would indicate the beginnings of boundary dominated flow, 1.2 BCF. If you hadn't done that analysis, I don't think that you would see that, because there's too much sort of noise and stuff built in there. So you can see why we're using the term reservoir signal extraction. We're hoping that there's something buried in there in terms of a reservoir signal. If we eliminate all the outliers and the noise operational problems that are in there, maybe we can see what's going on in the reservoir. That's the idea. Okay, so that's liquid loading. The productivity shifts are changes in the same slope, but offset in different places in the data. I won't show any examples for that, but it's pretty obvious in the data when you see that. The next section is transient flow diagnostics, and productivity diagnostics are things that happen, because of operational phenomenon or stuff that happens inside, dynamics that happen inside the wellbore or near the wellbore. Transient diagnostics are things that happen early in time. However, with the advent of very, very low permeability reservoirs, they may actually be things that happen it may take a long time to happen, because transient flow, as we get into lower permeability reservoirs, is being stretched out later and later in time. So these are actually becoming much more important than they used to be. I'm going to talk about the basic ones to start with, and then we'll maybe spend a couple of minutes talking about some more complex things. The basic ones that I really want to reiterate, and we've talked about them before, is there's three. There's general sort of radial flow. And I'm going to talk about radial flow a little bit in the sense that it's the expected flow regime in a conventional completion, medium to high perm reservoir. And what that means. So if we have a vertical well in the middle of a circle, and we've already seen the type curve model for that, we've got a vertical well in the middle of the circle, what we are going to get is convergent flow into that drain that sits in the center of that drainage area. That's our conventional reservoir model. That's radial flow. Okay? So you expect to see that in any vertical unfractured well that produces from a medium to high permeability reservoir. What does that look like on the type curve? Well, it looks like concave upwards. So it has a concave upwards appearance. It may show up as being lower with very slight concavity. It may have very severe concavity. It really depends on whether it's a damaged well or not. If it's a very highly damaged well, it will be very flat at the beginning. Okay, so this picture may change depending on how much damaged skin there is. So it's sort of a dynamic sort of thing. But the type curves do a very good job of replicating those different shapes that you'll see in the data. And you should be able to find the one that fits, provided that you have the right sort of data to begin with. So that's radial flow. When we get into tight and unconventional gas, we start to get into fracture flow. And fracture flow is linear flow. So instead of having this situation, we have the situation where we've got a fracture. So we don't get the convergent sort of flow lines coming into the wellbore. Instead, what we get is linear flow. Okay, and linear flow is just like it sounds. All the flow lines are parallel. The production response from these two, luckily for us, if we're trying to tell the difference between them, are very different. We can immediately tell one from the other. So we know whether we're getting a production response that's typical of a big fracture, or whether we're getting a production response that's typical of an unfractured well. So for example, if a service company has gone out and pumped a big fracture into a well, and we get a production response that looks like this, you can conclude that the fracture treatment was not effective. Okay? So when we do have these big fractures in these wells, the first diagnostic I want to do is make sure that I've got fracture linear flow. If I don't have fracture linear flow, then that tells me that there's, the completion didn't go properly, and for whatever reason I don't see the effect of that fracture. I should see the linear flow from that fracture if it's there. So what does that look like on the plot? Well, I'm showing it right here. It actually has on a Q over delta P versus material balance time plot, it should have a half slope. Okay? So if you were to measure it, it goes two log cycles across and 1 log cycle down. As opposed to a unit slope, which goes 1 log cycle across and 1 log cycle down. So you got to make sure that you separate fracture flow from boundary dominated flow. They're very different, right? This fracture flow has a much shallower slope. But it's different from radial flow also because it doesn't have upward concavity. So these are the things you need to be aware of. Okay, so that's fracture linear flow. One thing to sort of keep in mind is these pictures, it's not always as simple as it looks. For instance, what if this fracture were very small? And it doesn't necessarily have to be small. It just could be that I'm viewing it from further away. In other words, this fracture in a very, very large reservoir. Well, if you think about it, eventually I'm going to get the convergent flow lines on this fracture as well. Okay, even though it showed fracture linear flow at the beginning, if it's in a big infinite acting reservoir, I will get these convergent flow lines coming later on. So I may have a situation where I have fracture linear flow at the beginning and then upward concavity from radial flow that occurs later on. Okay, so there's nothing to say that I can't have both flow regimes occurring in sequence. Let me give you a different example that reverses these two flow regimes. Let's say I have a vertical well that's drilled in a channel, a reservoir that looks like this. In this case, I'll get radial flow at the beginning, but very quickly I'm going to hit the two boundaries on the side of the channel, and it's going to turn into linear flow in the late time. So this one is the absolute reverse of this situation. So transient analysis is actually quite interesting because you can use what you see on the production data plot here to piece together the flow regimes and probable geometry of the completion reservoir system together by fitting those two together. Okay? So maybe I didn't know ahead of time that this well was drilled in a channel, but if I see long-term linear flow in an unfractured well, it's a very good bet that I have a channel-type system, or at the very least a system that has a strong permeability in one direction over another, which a channel system will, because it'll be bounded on two sides, but open on the other two sides. So those sorts of things we can start to piece together just based on the sequence of flow regimes that we see in the data, what the system is actually going to look like. As it turns out, in a lot of tight and unconventional gas reservoirs, we don't see this at all. We see linear flow, and then possibly a immediate transition to boundary-dominated flow, or linear flow that just lasts forever. We very rarely see linear flow followed by pseudo-radial flow. So that's just something that's part of the observations, and we tend not to use this model as much. We use a model that's more consistent with linear and then a boundary, a completely bounded system. These are all things that we learn by looking at the data. They're not constraints that we enforce externally. They're things that come from looking at the data and trying to piece together what we're seeing. This idea of a transitionally dominated flow sometimes comes into play in that channel situation or in naturally fractured reservoirs where we have a strong permeability in one direction but not in other directions. And what it will tend to show up as is data that doesn't quite match with the type curves that we see. And will tend to overshoot on one side and undershoot on the other side. So it's a situation where the data doesn't quite match on the curves. So transient analysis is becoming tremendously important as we get into lower and lower permeability systems and systems that have large fractures. Okay, one final diagnostic that is important is the bad data diagnostics. And as we showed before, right at the beginning of this discussion, bad data may be more prevalent than you think. It may be bad simply because it's measured in the wrong location. If I measure the pressure downstream of a choke, when there's a big choke in place, I'm not going to get good quality pressure data. But there's other places where we can go wrong here. Usually, if it's an onshore well, the production rates are going to be good quality because that's what the company is getting paid on. It's the flowing pressures that could be questionable. So one of the places where it gives us the opportunity to make mistakes with flowing pressures is when we take a measured pressure and convert it into a calculated pressure, but we have to do that. We don't have a choice. But it introduces the possibility of making errors, and that's kind of what this is all about. So our flowing pressure may be measured at the wellhead, but we have to convert it using a nodal analysis. We have to convert it or calculate the pressure loss in the wellbore so we can convert it to a bottom hole or sand face pressure. If, when we do that, we made a mistake, any one of these mistakes, tubing size too large, initial pressure too high, wellbore correlations underestimate the pressure loss, we may end up getting a diagnostic that looks like this, and the data was supposed to be on that curve, but it didn't match there, so we're going to get the wrong answer. So just be aware of those sorts of things. When we're doing the calculations of pressure, there could be some problems introduced there. In the other sense, we could end up getting a shape of the data that looks like this. There's no reservoir effect that can cause that steep of a drop at the beginning. If it looks like this, it means that your delta P is off somehow. In other words, your pressure loss in your wellbore has been over-predicted in this case. So maybe the tubing was made too small, or the initial pressure was too low, or the wellbore correlations overestimate pressure loss. One example where wellbore correlations can overestimate pressure loss is when you have assumed that liquid condensates or liquid water rates were in the liquid form while they were flowing in the wellbore. Many times these fluids come out and are only fluids once they've been separated in the gas separator. In the wellbore, because we've got high temperatures, they may all be in vapor form. The problem is the data comes to us after it's been measured on the surface. So when we can reconstruct these pressure loss systems, we may overestimate the pressure loss because we think that there's all these liquids downhole. So these are the sorts of things that can happen. So we just need to be aware of potential problems that can be caused by bad data. And that basically wraps up the section on diagnostics.